Every headline this week said the same explosive thing. The world's biggest chipmaker just walked away from classical computing entirely, betting its entire future on quantum. Forums lit up, stock forums speculated, and if you take that headline at face value, you'd think silicon itself just became obsolete overnight. Here's the problem. That headline isn't quite true, and the real story hiding underneath it is actually more interesting and more strategic, and more revealing about where the entire chip industry is really headed than the exaggerated version anyone's been sharing. Read that again. The truth here is stranger and more useful than the myth. Let's start with what actually happened, because getting this right matters more than getting it exciting. And the honest version of this story still has plenty to offer. In early July of 2026, South Korean business outlet Seoul Economic Daily reported that Samsung, one of the two companies most people mean when they say the world's biggest chipmaker, is developing new simulation algorithms that lean on quantum computing and artificial intelligence to improve one of the most difficult, most expensive steps in the entire chip manufacturing process. Not replacing classical computing, not shutting down a single fab, not abandoning decades of silicon engineering overnight. Developing, testing, simulating is a genuinely important distinction. And if you stick with this video, you'll understand exactly why the difference between developing a new tool and dropping an entire technological foundation matters enormously, both for accuracy and for actually understanding where this industry is really going. Before we go any further, it's worth clearing up an easy point of confusion that even serious tech journalists sometimes trip over, because it changes who this story is actually about. When people say the world's biggest chip maker, they don't always mean the same company. Depending on which specific number you're measuring, that title could belong to Taiwan's TSMC, the company that manufactures more advanced chips for more customers than anyone else on Earth, producing over 17 million 12-inch silicon wafers in 2025 alone, up from 13 million just 5 years earlier. Or it could belong to Samsung, which is frequently ranked as the world's largest chipmaker by total semiconductor revenue, once you combine its memory chip business with its foundry operations. This isn't a trivial detail buried in a footnote. It's actually central to getting this story right, because the company genuinely reported to be experimenting with quantum-assisted chip design isn't TSMC at all. It's Samsung, and specifically, it's not even Samsung's core chip manufacturing division doing this work directly. It's Samsung SDS, the company's digital and IT services arm, the part of Samsung that handles software, cloud infrastructure, and advanced computing projects, rather than the physical business of etching circuits into silicon wafers. So what is Samsung SDS actually building? And why does it matter enough to make headlines at all, even without the exaggeration? To understand that, you first need to understand the single hardest, most consequential step in the entire process of manufacturing a modern computer chip, a step called lithography. Think of lithography as the blueprint stage of chip manufacturing. Except instead of drawing blueprints on paper, engineers use extraordinarily precise machines called scanners, manufactured almost exclusively by a single Dutch company named ASML, to project the intricate circuit patterns of a chip directly onto a silicon wafer using ultraviolet light. Every transistor, every wire, every microscopic feature that will eventually let your phone process information or let an AI data center train a massive language model, its physical existence right here at this exact stage. Get lithography wrong, even slightly, and the consequences ripple through everything downstream. Chips come out with defects, yields drop. Entire batches of expensive, carefully manufactured silicon become unusable scrap. According to the reporting on Samsung's project, the company is specifically trying to improve two things through this new quantum and AI approach. Chip density, meaning how many transistors you can pack into a given area of silicon, and yield, meaning how many of the chips coming off a single wafer actually work well enough to sell. These aren't abstract academic metrics. In the brutally competitive foundry business, where Samsung has spent years trying to close the gap with TSMC, small improvements in yield and density translate directly into billions of dollars in either profit or lost revenue. Features on a silicon wafer before any actual manufacturing happens. Once that simulation is complete, artificial intelligence takes over the next stage, scanning through the simulated results to detect and correct errors before they ever show up in a real, physical, extremely expensive batch of chips. Think about what that combination is actually trying to solve. Quantum computing handling the fiendishly complex physics simulation. Classical AI handling the pattern recognition and error correction on top of it. This is not one technology replacing another. This is two fundamentally different tools, each doing the specific job it's naturally suited for, working together inside the exact same manufacturing pipeline. And crucially, according to the sourcing behind this story, Samsung's own timeline confirms just how early stage this entire effort still is. The company is reportedly aiming to run a proof of concept, not a finished product, not a deployed manufacturing process, but an initial test to see whether the underlying idea even works, sometime in 2027. Read that again. We're not talking about something running in Samsung's fabs today. We're talking about a concept the company hopes to formally test more than a year from now. This is precisely the moment in the story where an honest documentary has to slow down and ask the harder, more useful question. If Samsung's actual quantum computing initiative is this early stage, this narrow in scope, and this far from deployment, why did headlines this week claim the world's biggest chipmaker had already dropped classical computing entirely? The answer says less about Samsung's actual roadmap and more about how technology journalism sometimes works in an attention economy that rewards the most dramatic possible framing over the most accurate one. A modest, genuinely interesting R&D story about exploring quantum simulation for one specific manufacturing step got quietly transformed, somewhere in the retelling, into a sweeping claim about an entire industry abandoning the foundation it was built on. This is not chaos. This is strategy of a very specific, very familiar kind, the kind that trades precision for clicks. And it happens constantly in coverage of quantum computing specifically, a field that already sits at the exact intersection of genuinely mind-bending science and irresistibly exciting marketing language. But here's why you shouldn't just dismiss this story as pure hype and move on, because underneath the exaggerated headline sits a genuinely fascinating, scientifically well-grounded reason why quantum computing might actually help with chip manufacturing simulation, and understanding that reason tells you something real about where this technology's actual strengths lie. Classical computers, even the most powerful supercomputers on Earth, run into a brutal mathematical wall when they try to simulate certain kinds of quantum mechanical physics in extreme detail, and chip manufacturing physics increasingly bumps directly into that wall. Consider a striking, very recent example that illustrates just how demanding this kind of simulation has become. In March of 2026, a team of researchers used 7,000 individual graphics processing units, essentially an enormous cluster of classical computing power, running a specialized simulation platform called Artemis, originally developed under the United States Department of Energy's exascale computing project, just to simulate a single tiny quantum chip in extreme physical detail. 7,000 GPUs. 7,000 GPUs for one small chip. Think about what that scale actually implies about the computational cost of accurately modeling quantum mechanical behavior using purely classical methods. This is exactly the kind of exponential computational wall that makes quantum computing theoretically attractive for simulation tasks in the first place, because the underlying mathematics shows something genuinely elegant and genuinely frustrating at the same time. According to peer-reviewed research on this exact problem, classical simulation resource requirements for quantum systems scale exponentially, not just with the number of quantum elements you're trying to simulate, but with the number of energy levels included for each one, for a specific common type of quantum bit called a superconducting. Transmon, accurately capturing its behavior, typically requires modeling around 16 distinct energy states just for that single qubit. Now, stack 16 possible states for every additional qubit in a system, and you get a mathematical space that grows so explosively large, so quickly, that even the most powerful classical supercomputers on the planet eventually simply run out of road, unable to keep up no matter how much raw computing power you throw at the problem. This is precisely the kind of exponentially scaling computational wall that quantum computers are theoretically well suited to help break through, because quantum systems can, in principle, represent and manipulate these same kinds of exponentially large mathematical spaces far more naturally and efficiently than classical hardware ever could. And it's worth pausing here to note that this isn't some brand new speculative idea invented specifically for Samsung's lithography project. Researchers have been exploring what's sometimes called quantum computer-aided design for years now, essentially asking whether a quantum processor could help simulate and validate the physical design of the next generation of quantum processors, mirroring the exact same relationship that's existed in classical computing for decades, where today's chips are routinely used to help design and simulate tomorrow's more advanced chips. There's a genuinely compelling historical parallel here worth understanding, because it helps explain why serious engineers, not just marketing departments, take this idea seriously. Back in the 1970s, the entire classical chip design industry underwent what engineers sometimes call its SPICE moment, named after a piece of software called Simulation Program with Integrated Circuit Emphasis, which shifted circuit design away from a process dominated by individual engineers' hard-won experience and manual approximate calculations toward a far more rigorous, far more scalable engineering discipline built on precise device models, mathematical circuit equations, and systematic numerical simulation. That single shift eventually gave rise to the entire modern field of electronic design automation, the sophisticated software tooling that makes today's staggeringly complex chips even possible to design at all. According to recent academic analysis, the quantum chip industry today sits at a remarkably similar inflection point, still relying heavily on manual electromagnetic field simulation and design rules accumulated informally within individual research groups, rather than the kind of mature, industrialized, simulation-driven engineering discipline that transformed classical chip design half a century ago. Samsung's quantum lithography experiment, whether or not it ultimately succeeds, fits directly into this much larger, much more credible pattern of an entire industry searching for its own version of that same foundational shift. Now, it's worth taking a moment to separate this story clearly from a different, closely related thread that gets easily tangled up with it in less careful reporting. Because conflating these two ideas is exactly the kind of mistake that produces misleading headlines like the one that inspired this video. There is a meaningful difference between using quantum computing to help design ordinary classical silicon chips, which is what Samsung is reportedly attempting with its lithography simulation project, and using quantum computers to help design future quantum chips themselves, which is an entirely separate, equally active area of academic and industrial research. Both of these are genuinely happening right now in different labs, pursued by different teams for different reasons. But they are not the same story, and treating them as interchangeable the way sensationalized headlines often do only adds to the confusion rather than clarifying anything. This video is specifically about the first kind, quantum-assisted simulation aimed at improving how we manufacture the ordinary silicon chips, already running in your phone, your laptop, and every AI data center currently straining the world's power grids. Here's another detail worth sitting with, because it reveals just how enormous the gap still is between the size and maturity of the classical chip industry and the entire quantum computing industry combined, a gap that makes the idea of quantum replacing classical computing anytime soon look almost absurd once you actually look at the numbers side by side. Remember that figure from earlier, TSMC alone producing over 17 million 12-inch silicon wafers in 2025. Now compare that staggering industrial output to the entire global quantum computing market, which, according to current industry estimates, is valued at only about $1.44 billion, with only modest growth expected through 2026. Read that again and really let the scale of that difference sink in. The entire worldwide quantum computing industry, every company, every processor, every research contract combined, is worth a small fraction of what a single classical chip manufacturer generates through ordinary silicon production in a single year. This is not the picture of an industry on the verge of replacing its predecessor. This is the picture of a genuinely promising but still profoundly early-stage technology, one that remains almost comically small next to the industrial giant it supposedly just dropped. And this size gap becomes even more meaningful once you understand who's actually building the physical hardware that makes quantum computing possible in the first place. Because even here, classical chip manufacturing infrastructure remains deeply, structurally essential rather than obsolete. Consider a company called Quantware, which industry press has explicitly nicknamed the TSMC of quantum computing, precisely because of the specific role it plays in this emerging supply chain. In May of 2026, Quantware raised $178 million in a funding round led by Intel Capital, alongside investors, including IQT and ETF partners. Crucially, Quantware doesn't build complete quantum computers itself. Instead, it manufactures quantum processing units, essentially quantum chips, using a superconducting architecture similar to the approach pursued by Google and IBM, then sells those chips to universities, startups, and national laboratories that want to build their own quantum hardware without starting from scratch. Alongside this funding round, the company unveiled a new processor architecture called VIO-40K, designed to support quantum chips containing up to 10,000 qubits, roughly 100 times larger than most of today's leading commercial designs. The company plans to use its new funding to build something called KiloFab, envisioned as the world's largest dedicated open architecture quantum fabrication facility, expanding its production capacity by roughly 20 times over. This is genuinely exciting, genuinely significant progress for the quantum computing industry specifically. But notice what it actually represents: a specialized purpose-built quantum chip factory, entirely separate from and dramatically smaller in scale than the classical semiconductor manufacturing ecosystem that companies like TSMC and Samsung have spent decades and hundreds of billions of dollars building. Quantum computing isn't outgrowing classical chip manufacturing. It's still, quite literally, building its own much smaller house next door. There's an even more direct, almost ironic connection between the classical chip industry and quantum computing worth understanding here, one that further undercuts the entire premise of the exaggerated headline that inspired this video. TSMC, the very company most people probably assumed was the actual subject of a story about the world's biggest chipmaker dropping classical computing already manufactures a specific category of quantum-related chip today, using its completely ordinary, unmodified classical manufacturing processes. A company called Quantum Emotion has used TSMC's standard 65 nanometer CMOS fabrication process, the same kind of everyday manufacturing technology used for countless conventional chips, to produce something called a quantum random number generator chip, a specialized component that exploits a genuine quantum physical effect called electron tunneling to generate truly random numbers for cryptographic security applications. This is real. This is happening today, not in some speculative 2027 proof of concept, but look closely at what it actually represents. A tiny specialized product category manufactured using entirely conventional classical chip-making equipment and processes that happens to exploit one narrow quantum physical phenomenon for one specific security application. This isn't TSMC pivoting away from classical computing toward quantum. This is classical manufacturing infrastructure quietly, usefully, serving a small corner of the quantum-adjacent world. Exactly the kind of practical, unglamorous collaboration between these two technologies that rarely makes headlines precisely because it isn't dramatic enough to click on. So, where does the honest, carefully researched version of this story actually land once you strip away the exaggeration and look squarely at what credible experts and industry analysts actually believe is coming? The overwhelming consensus across the field points toward hybrid coexistence, not replacement, and understanding exactly why experts keep landing on the same conclusion tells you almost everything you need to know about quantum computing's realistic near-term future. Industry analysis consistently describes quantum chips as being suited to specialized roles, tackling optimization problems with astronomically large solution spaces, simulating molecules and materials with a level of quantum mechanical accuracy classical computers structurally struggle to match, potentially accelerating certain narrow categories of machine learning and handling specific cryptographic tasks. Meanwhile, classical computers continue handling the overwhelming majority of everyday computational tasks far more efficiently than any quantum system currently can, or, according to most serious physicists, ever realistically will. One particularly blunt industry analysis published in November of 2025 put this dynamic about as plainly as possible, stating that even in what it called a fully quantum future, classical chips remain dominant by sheer volume and practical necessity. Quantum computers themselves, every single one currently operating anywhere in the world, depend entirely on sophisticated classical control chips just to function at all. Chips that are typically manufactured using exactly the same kind of advanced extreme ultraviolet lithography techniques that companies like TSMC and Samsung have spent decades perfecting. Quantum computing isn't making classical chip manufacturing obsolete. Quantum computing is, quite literally, built directly on top of it, dependent on the continued advancement of classical manufacturing infrastructure in order to function at all. Think about what that dependency actually means for the entire premise of a headline claiming any chipmaker has dropped classical computing for quantum. It would be a bit like a construction company announcing they've abandoned steel and concrete entirely in favor of glass, while somehow failing to mention that the glass windows they're now exclusively using still need steel frames and concrete foundations to actually stay standing. The relationship between quantum and classical computing isn't a story of one technology replacing another. It's a story of one technology being carefully, deliberately built as a specialized extension sitting on top of the other, dependent on it, supported by it, and destined, according to every credible expert currently working in this field, to coexist alongside it rather than replace it for the foreseeable future and quite possibly for the rest of your lifetime. None of this means Samsung's actual research effort deserves dismissal, though, and it's worth closing this story on genuine, well-earned optimism rather than pure debunking, because there really is something worth watching here. If Samsung's proof of concept succeeds sometime in 2027, and if the underlying quantum simulation approach genuinely proves capable of meaningfully improving lithography, yield, and chip density beyond what purely classical simulation methods can currently achieve, that would represent a real, tangible, commercially significant application of quantum computing, arriving years earlier than most of the field's more dramatic, headline-grabbing promises, things like breaking encryption or fundamentally transforming artificial intelligence training, which remain, by most credible expert estimates, considerably further out on the horizon. There's something genuinely fitting about that possibility, too, if you think about it. Perhaps quantum computing's first truly meaningful commercial contribution to the modern technology economy won't arrive through some singular dramatic breakthrough moment, a headline event capturing global attention all at once. Perhaps it arrives quietly, incrementally, embedded inside one narrow, unglamorous step of an already existing industrial process, improving chip yield by a few crucial percentage points here, Sharpening a lithography simulation there, exactly the kind of modest, compounding behind-the-scenes progress that rarely makes for an exciting headline, but that genuinely moves an entire industry forward, one careful, well-verified step at a time. If you want to understand what actually happens when Samsung's proof of concept comes due in 2027, and whether this quiet, methodical approach to quantum-assisted chip manufacturing ultimately proves more consequential than any of the more dramatic quantum computing headlines currently dominating the news cycle, that's exactly the story we'll be tracking closely as it continues to develop. So make sure you're subscribed before that verification finally arrives. Before you go, I want to know what you honestly think about a story like this one. Does the gap between today's exaggerated headline and the far more modest, far more carefully qualified reality change how you'll read the next big quantum computing announcement that crosses your feed? Or do you think, even in its more modest, accurately reported form, Samsung's quantum lithography experiment still represents a genuinely important signal about where this entire industry is quietly, patiently headed? Leave your honest answer down in the comments below, and as always, I read every single one.